Okay, so in this video we're going to talk about free body diagrams. Free body diagrams, or FBDs, as I call them, are basically something that you're going to include with most of your problems for the next couple months at least. And so this is just something that you need to become very familiar with and comfortable with, and so we're going to do lots of practice. But basically a free body diagram, the purpose of a free body diagram is used to kind of diagram what force or forces are acting on a given body, on a given object, I should say, in what direction are those forces and what is their relative magnitude. Okay, and so here are basically the steps for drawing an FBD. Okay, step 1, you draw the object as a dot, just so you don't spend a lot of time, making your picture all pretty. Step 2, you identify what force or forces are acting on the object based off of context clues. We'll talk more about that on the next slide. Step 3, you identify whether or not the object is accelerating, because whether or not it's accelerating depends on how you draw the free body diagram. As we talked about in the last video, over Newton's first law, if an object is accelerating, that implies that a net force must have acted on that object. Okay, and so if you know in the situation, in the problem, that the object is at rest or moving with a constant velocity, that tells you that the net force on that object must be 0, and so that impacts how you draw the FBD. Okay, and then to actually draw the free body diagram, you're basically going to draw an arrow for each force acting on the object. Remember, a force is a vector, and we draw vectors as arrows. Okay, so you draw an arrow for each force acting on the object, with the length of the arrow representing the relative strength of that force. Okay, always make sure when you draw your FBDs that you draw the arrows going away from the dot. Okay, now before we get into doing some examples, and I think I'll do maybe like 4 or 5 examples just so you can see what these look like. This is one of those things that's really, really basic and not difficult at all, but there's some subtle things that you have to be careful about. Okay, so before we get into this, make sure you take really, really good notes, because here I'm going to talk about the different types of forces, and this is not like a comprehensive list of every possible force in the universe, but just the most common forces. Okay, so let's start with weight. Okay, the force of gravity, Fg, aka an object's weight. Okay, so the force of gravity is a downward force for all objects near the surface of a planet. Notice that all is in bold, all means all. Okay, so when you're drawing an FBD, most people usually start with the force of gravity going down because that's a given. Unless your situation takes place in space or something like that, all objects close to the surface of a planet, that means not in space, have a downward force of gravity. Okay, so that's the most common one to see, because basically every object is going to have force of gravity on it, unless, like I said, it's in space or something. Okay, the next one, and again, make sure you're taking really good notes here, is what's called the normal force. Okay, now read carefully what it says. It is a reaction force of a surface. Surface is underlined. Okay, the reason it's underlined is any time you ever have an object touching a surface, you have a normal force. Okay, now the word normal, in this context, normal is a mathematics term. You've probably never heard it in math class before, but it is a mathematics term, and normal means perpendicular. I don't know why the math people have more than one word for the same thing, but there you go. Okay, so the normal force has its name because it's always perpendicular to the surface that's acting on. Let me give you an example. If you press your hand against the wall, okay, your force is pushing, or your hand is putting a force into the wall. The force that stops your hand from going through the wall, that's the normal force. Okay, that's the force coming out from the wall, pushing against your hand. When you stand on the ground, the force that keeps you from falling down into the earth, that's the normal force. Okay, that's the force from the ground acting up on your body. Okay, so it's the reaction force of something touching a surface, and it always acts perpendicular to the surface. Okay, next we have tension. Okay, Ft, the force that a rope or string exerts on an object. as you're taking these notes, by the way, I'm telling you these things so that you have like a basis for using context clues in a problem. So if you're reading a problem and it says, Jimmy is dragging a box with a rope, the first thing you should think about is, hey, there's a rope. That means there's a force of tension. Okay. Hey, the box is on a surface. That means there's also a normal force. Okay, that's why it's really important that you take really good notes here, because you're going to be using what's on this slide to help you identify what force or forces are acting on a given object. Okay, so you have tension when you have a rope or a string. Friction is a force caused by two surfaces rubbing together, acts to oppose relative motion. Now that is basically a fancy way of saying that friction opposes motion. So if an object is moving one way, friction is acting in the opposite direction. Let's say even if the object doesn't actually move, if it's trying to move one way, friction acts in the opposite direction that it's trying to move. Alright, so if I try to push a box to the right, whether or not it moves, there's still a force of friction acting to the left. Now there's two types of what's called dry friction, okay, as opposed to wet friction, which is when you have some type of wetness or slickness between the objects. We're not going to talk about wet friction in this class. Okay, but dry friction comes as either static or kinetic. And so we use subscripts to indicate different types of friction. For kinetic friction, we write FFK, okay, force of friction kinetic. We would say that's the force of kinetic friction. And for static friction, we put FFS for static friction. Now, what's the difference? Well, if you push on something and it doesn't move, okay, it's probably being acted upon by static friction. Static means not moving or not changing. Okay, so you have static friction when the object is not moving. So let's say, there's a really, really heavy box outside. I push it, I try to move it, but it's so heavy that it doesn't actually move. The force that's opposing my push is static friction. Okay, let's say I, really dig deep and I give it all I've got and I push really hard and the box just starts to move. As soon as it's moving, that's when it's kinetic friction. Okay, so kinetic means motion. You have kinetic friction acting whenever the object is moving. Okay, and then applied force is just a generic term for when, a person or an object is like directly applying a force. Okay, so in the example I gave before, if I'm pushing on a box, I'm probably calling that force my applied force. And then spring force, Fs, that's when you have like a spring or rubber band, and there's a force acting because of that. And if it's not one of those forces, just give it an appropriate label. So for example, if there's like a rocket blasting off, and there's a force from the rocket, that's not one of these forces, right? And so I'd probably just label it like, F rocket, or something that makes sense in the context of the situation. Again, this is not every single force you might encounter. If it's not one of these forces and it doesn't really fit into the category of what we talked about before, just give it a name and a label that makes sense. Okay, so pause there and make sure you've got that in your notes. Okay, just some really important extra notes before we get into these FBD examples. Okay, make sure that when you're drawing a free body diagram, you do not draw net force on a free body diagram. Remember, the net force is the sum of the forces acting on that object. Okay, net force does not go on a free body diagram. Velocity, acceleration, things like that do not go on a free body diagram. The only thing that should be on an FBD are forces. I should also mention a free body diagram does not show you which way an object is moving. It has nothing to do with that. An FBD shows you nothing more or less than the forces acting on an object. And down here you can just read a couple more hints. Use context clues. By definition, an object in free fall is only acted upon by the force of gravity. We've talked about free fall before, but here for the first time you see the actual definition. An object in free fall, by definition, the only force acting on it is the force of gravity. an object moving on a rough surface is going to feel a frictional force. If you're doing a problem and it says such and such object moves along like a smooth surface, that's a context clue telling you that, hey, there's probably not any friction acting. Okay, so these are all little context clues that you can use to help you draw FBDs. So with that being said, let's get into it and let's look at some examples of free body diagrams. So example 1 says a book is at rest on a tabletop, diagram the forces acting on the book. So in my mind, I'm going through my mental checklist of what forces might be acting based on the situation. Okay, now I know that the book is not in space. Okay, it's probably like, close to the surface of a planet, which means that there's a force of gravity acting down. I shouldn't have to say this, but guys, please don't forget force of gravity goes down, not up. Okay, sometimes people have gravity going like at weird angles. Force of gravity goes straight down. Then I run through the checklist of forces in my brain. Okay, is there a surface? Well, yeah, because it's on a tabletop. That's a surface. If anytime you have a surface, you have a normal force. Okay, so you have Fn. By the way, don't confuse Fn, which is normal force, to F net, which is net force. Two completely different things. So I'm running through my checklist. There's no rope or string, so there's no tension. Is the book trying to move? Okay, is anything pushing on it? Is it trying to move? Is it actually moving? No. That means there's probably not any friction. Okay, there's nothing pushing on it, so there's no applied force. I think these are the only two forces acting. Now look what it says right here. A book is at rest. Because of Newton's first law, if an object is remaining at rest, that tells you immediately that, hey, the net force on the object must be 0. So when I draw the normal force here, I'm going to draw an arrow going up that is the same length as the force of gravity going down. The length of the arrow tells you the relative strength of the force. Now, I don't know like how many newtons each of these forces are, but the longer the arrow, the bigger the force. In order for there to be a net force of 0, these two forces have to cancel each other out. Okay, so when I'm looking at your FBDs, I'm looking at number 1, did they draw it correctly? Number 2, did they label it correctly? And number 3, are the lengths of the arrows correct? Okay, because if you are drawing this FBD on a test or a quiz and the top arrow is longer or shorter than the bottom arrow, I'm taking points off. Okay, they must be the same length for this example because the object is at rest and therefore the net force is 0. Okay, so let's take a look at example 2. Okay, example 2 says a skydiver is falling with a constant velocity. Consider air resistance. That's a big old context clue saying, hey, there's air resistance. Alright, so here's a dot to represent the skydiver. I think through my mental checklist of what forces are acting, probably have force of gravity that goes down. Is there a surface? Well, hopefully not, because he's falling through the air, so there's no surface. That means there's no normal force. There's no rope or string, so there's no tension. You don't have like two solid surfaces touching each other, so there's no friction either. But it does say that there is air resistance. Number 1, it says there's air resistance. And number 2, think back to the first law. The only way for an object to move with a constant velocity is that the net force on the object is equal to 0. Okay, Newton's first law. An object in motion remains in motion at constant velocity unless acted upon by a net force. So even if it didn't say consider air resistance, looking at the FBD, there has to be some other force balancing out Fg in order for the net force to be 0. Okay, so notice I draw an up arrow representing the same length, so when I add these two forces together, they give me a net force of 0. Now, what would I call that force? Well, it wasn't really on my list, and so I'm just going to call it, let's see, what makes sense? F air for air resistance. And there we go. Okay, that is my FBD. Alright, let's do a few more quick examples. Example 3. A man using a rope Boom, context clue. Rope or string, there's got to be tension somewhere. Drags a sled to the left across a rough surface. Another context clue. That's telling us that there's friction. Now, what type of friction depends on is it moving or not? Well, it says the man is dragging it, so yeah, it's probably moving. So that's most likely going to be FFK for kinetic friction. And he's dragging the sled to the left with a constant velocity. Again, context clue. Newton's first law. Object moving at a constant velocity must have a net force of 0. Alright, so now I draw my dot. I run through my mental checklist a little bit faster now. I got the force of gravity going down. Is the sled on a surface? Yes, that means there's a normal force. In this case, the surface is the ground. Is there a rope or string? Yes, so there's tension. Okay, is there friction? Yes. Is there anything else? Okay, you might say, well, isn't there an applied force? Well, the force is being applied by the rope. So an applied force would be like the man physically putting his hands on the sled and pushing it. Okay, in this case, the force from the man is transmitted through the rope, so we just have tension. So what does this FBD look like? Force of gravity going down, normal force going up, same length arrow. Because when I'm looking at these two arrows, I see they're the same length, I'm thinking net force is 0. Now, which way is tension? Well, he's dragging the sled to the left, so I want tension to the left. Now you might say at that point, why is my arrow so long? Okay, doesn't it have to be the same length as the other ones? Well, not exactly, because what happens is when we add up the forces, when we do the sum of the forces, these y forces only affect each other, and the x forces only affect each other, kind of like in projectile motion. You keep the x stuff and the y stuff separate. So I need a net force of 0, but that only means that my two y forces have to balance each other out, and then my two x forces also have to balance each other out. So if I have ft to the left and it's this long, in order to give me a net force of 0, I have to draw my force of kinetic friction the same length going in the opposite direction. And I know force of kinetic friction acts to the right because friction always opposes relative motion. Okay, so pause it there if you need to look at that some more. Okay, and let's do one more example and then we'll be done with this video. A man standing in an elevator accelerates upwards. Make sure you understand, by the way, accelerating up and moving up are not the same thing, because acceleration has nothing to do with velocity. It has to do with change in velocity. Okay, so just keep that in mind. When it says he's accelerating up, we don't know if he's actually moving up or not. Alright, so think about the forces on the man. And if you have to, draw a picture. Pictures are always helpful. So here's a man in an elevator. Hey, now, obviously he's got force of gravity acting on him. Okay, is there a surface? Yes. Okay, if there's a surface, there's automatically a normal force. Now at this point, somebody's going to say, well, isn't there tension at the top of the elevator? And that's true, and if we were drawing the free body diagram for the elevator itself, we would include that tension. Okay, but the cable at the top of the elevator is not touching the man, therefore it does not go on the free body diagram for the man. Okay, it would go on the free body diagram for the elevator though. So in this case, we only have these two forces. Because he is accelerating up, that means that the net force, number 1, is not equal to 0, because he's accelerating, and number 2, the net force must be up. And so when I draw this FBD, I need to make sure that Fn going up, out from the surface, perpendicular to the surface, that's the elevator floor, I need to make sure that arrow is longer than the force of gravity, like this. Okay, so this is what the FBD would look like for example 4. Now, does this mean that the man is moving up? No. Okay, because you can be accelerating one way and moving in the other way. Think back to the free fall unit. If you throw a ball up into the air, the ball can be moving up, but still have an acceleration due to gravity that acts down. Okay, so if he's accelerating upwards, that means either he's moving up and increasing in speed, or he's moving down and decreasing in speed. So remember, the free body diagram does not tell you which way an object is moving, only which way the forces on the object are acting. Now, what if, just hypothetically speaking, what if it said a man standing in an elevator moving up at constant velocity? Okay, well, if he's moving up at constant velocity, that means his net force is 0, and that basically means that those two forces would be balanced. If the man standing in an elevator was accelerating down, that means the force of gravity would have to be longer than the normal force error. Okay, so hopefully you're starting to see kind of how the first law plays a role in drawing FBDs. Okay, so we're going to stop it there for now. We'll try to do some more examples in class, and you'll have lots of examples on a practice worksheet that we'll see later on. As always, please let me know if you have any questions, and I'll see you guys in the next video.